Section 9.6, we're going to talk about the ratio and root tests. And we're actually going to spend a couple of days on this. We're going to finish the tests themselves today in class. They're fairly brief to talk about and give you a couple examples of. But we're going to do some work with them on the boards. And on Wednesday, we're going to do more extensive work with all of them on the boards. Yes, sir?
Will the work be part of the homework?
Yes, it will. So you'll be doing part of your homework in class. Always a good thing, right? Time saver and stuff like that. Yeah. So we'll be working examples of all of the different types of tests in class on Wednesday and a little bit today. So we'll start with the ratio test. Forget it. So this is Theorem 917. And we're going to start with non-zero terms. So let the summation of a sub n be a series with non-zero terms. And there are three things then that could happen. So the series, summation of a sub n, could converge absolutely. So it converges absolutely when the limit as n goes to infinity of the ratio of a sub n plus 1 over a sub n is less than 1. So if we have our limit of consecutive terms being less than 1, the series will converge absolutely. The series, summation from a to n, diverges when the limit as n goes to infinity of a sub n plus 1 over a sub n is greater than 1 or equal to infinity, which is technically greater than 1, but your book expresses it in both ways, so I decided to keep with what they did. And then the third option is that the ratio test basically doesn't work. So here's what it says. The ratio test is inconclusive. When the summation from n equal 1 to infinity, or well, the summation of a sub n, we just did it this way. Sorry, I'm not writing this right. Limit, there we go. Limit as n goes to infinity of a sub n plus 1 over a sub n is actually equal to 1. So basically what this is telling you is that you could try the ratio test and find out at the end of doing it that it was for nothing because it didn't work, right? That's really what it says. But if in fact you find that the ratio is less than 1 or greater than 1, you're good to go and you know whether it converges or diverges. And so we're going to do an example. So we're going to determine the convergence or divergence of the series. And the first one we're going to look at is the summation from n equal 1 to infinity, negative 1 to the n, of 6 over n factorial. All right, so first bit of information. Factorials tend to work really nicely with ratio test. Okay, so we're going to have a page in your book, I'm going to reference it here in a little bit, but that kind of gives you clues as to which test might be useful in certain situations. You've done some homework on that, right? I mean, we did some on the boards, had you do some homework on trying to decide which test would be good to use in this particular situation. So this is an example of one where you see factorials and you should be led to think ratio test right away, okay? So we're going to try the ratio test with this and you can see how it works. So the limit as n goes to infinity, and we're doing a sub n plus 1 first. So that would be 6 over n plus 1 factorial. And I want to divide it by 6 over n factorial, but division of fractions by fractions is often easier to do if we simply multiply by the reciprocal. So this would be n factorial over 6. Everybody good with that? Multiply by the reciprocal. We really divided, but... Oh, it's a good question. Does anybody know why I don't need to use it? Ethan? It is alternating series. That's not exactly why, David.
The absolute values.
Yeah, the absolute values are going to make it not necessary. Good question. I didn't think to mention it, but you're exactly right. It's because of the absolute values. Is everybody good? Make sense so far? Excellent. So our goal, of course, is to get this to simplify and for us to be able to do the limit pretty quickly. So clearly the 6's are going to reduce. And the wonderful thing, some of you are even nodding when I mentioned that this is a good test to use with factorials. Because what really happens with factorials, of course, is if you write them out, so here's n factorial now on the numerator, and I have n plus 1 factorial, and it's really the same as n plus 1 times n. And then I could do n minus 1, and then n minus 2, and so forth, right? And the beautiful thing when I'm dealing with factorials is that once the factorial and the numerator and the denominator match, then they can cancel out. They reduce or divide to 1. So what I end up having at this point is simply 1 over n plus 1. So what happens as the limit of, what is the limit as n goes to infinity of 1 over n plus 1? It's 0, right? And 0 is clearly less than 1, right? So what does that tell me? Oops. Does it converge? Does it diverge? What do we know? It converges absolutely, exactly. It's the first possibility, I guess, in my theorem above. So by the ratio test, this is the part that some of you are forgetting to do in your homework, so make, highlight it or something. By the ratio test, the summation from n equal 1 to infinity of 6 over n factorial converges absolutely. Oh, because I am being careless. Let me go back and put it in. Thanks. Better. Although my statement about it without the negative one of the n is actually true as well. But yes, that's better. Okay. Any questions? It's all good? Okay, let's do another one. Same directions. We've got the summation now from n equal 1 to infinity of n times 6 over 5 to the n. And we're going to do again the limit as n goes to infinity. And because I have a fraction involved, it might be also useful to see it written in reciprocal form. But we're going to do n plus 1. I'll write it out this time, division first. 6 fifths to the n plus 1 over n times 6 fifths to the n. We'll just write out that way to start with. Okay, so I have n plus 1 of the factor 6 over 5 in the numerator, and I have n of the factor 6 over 5 in the denominator. How are these going to reduce? Don't everybody yell at once. Right. So I'm going to have the same n plus 1 here. I'm going to end up with a 6/5 on top. Or you can multiply it at the back if you prefer. I'll kind of write it out to the side like that, and you have this. Right? There's one more of those factors on top than there was on bottom. So there's just one remaining once I divide things out. Does this make sense to everybody? Okay. Yes, sir?
Parentheses around your n plus 1 on the first.
You do if you're writing it like this. This is how I was thinking of it. It's more like this. So technically, it wouldn't hurt anything, of course, to have them there. But that's how I was thinking about it as I was writing. Yeah.
Top one.
Oh. Here. Yeah, that would be a good idea. Thank you. Yes, yes. Okay. You guys are just catching all my mistakes today. You're doing great. Excellent, excellent job. Okay. The 6/5, ignore it for the moment. N plus 1 over n. What is that approximately equal to? 1. That's limits 1, right? So we know that this is actually going to give me a limit of 6 over 5, correct? Yeah. So in terms of like algebraically proving that, the way that we've done that is by multiplying by 1 over n, top and bottom. So we'll do that real quick. That'll simplify out for us very nicely. So we end up with 1 plus 1 over n over 1, and I've got my 6/5 here. And I don't really need the absolute values because nothing's negative at this point, but this piece, of course, goes to 0. So the limit ends up being 6 over 5. Now, compare that back to what the ratio test said. What does that now mean? It diverges because that's bigger than 1, right? Yeah. So, again, we need to state that. We're going to say, by the ratio test, the summation of n times 6/5 to the n equal 1 to infinity, diverges.
So does this basically have the same relationship as the nth term test with the limit?
Well, so the nth term test has to do with determining whether something diverges only, right? So if the nth term goes to 0, right, for a sequence, it doesn't necessarily mean it converges. It just means it might. It's almost like it's inconclusive if it doesn't, diverge. It can tell you if it diverges, but not tell you if it converges. This is better because it can tell you if it converges, diverges in most cases. And then there's this one case, of course, the third one there, where if it equals 1, you need to go back and try a different test. It's just not going to work for this particular problem. So, yeah. Okay? Okay, got a pretty good handle on ratio tests. Look okay? Okay, the next one we're going to look at is the root test. So this is Theorem 918. And it says the following. It's going to sound and feel very familiar in terms of the conclusional statements. The series, the summation of a sub n, converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n when that happens to be less than 1. The series diverges when the nth root, I'm sorry, that's missing in my notes, but the limit as n goes to infinity of the nth root of absolute value of a is greater than 1, or infinite. And what do you think is going to happen when it equals 1? It's inconclusive. You got it. The root test is inconclusive when the limit as n goes to infinity of the nth root of a sub n is equal to 1. And you probably already know this, but by inconclusive it means that some of the time it will converge even though it equals 1, and some of the time it won't converge even though it's equal to 1. And some of the time it'll conditionally converge, which is a third option that's not even addressed in this particular scenario because we're dealing with absolute values. So, all right, so we're going to do the same thing we did in the last one. We're going to do a couple of examples of the root test so you guys can get a feel for how it looks. Same directions. We're going to determine the convergence or divergence of the series. And the one we're going to look at is the summation from n equal 1 to infinity of 4n over 5n plus 1 to the power n. So, on the last problem, I mentioned that it was very friendly when you see factorials, because factorials are sort of like a red light that says, or a green light that says, ratio test. Powers of n, right? Kind of scream root test. But even as I say that, you might think, but now wait a minute, that last example that you did had a power of n, and it did. So it doesn't always, go that direction. This one had a problem because we had the other n coefficient, right? Or not coefficient, but multiplying factor, which would have created problems to use the root test. But this example, as you can see, doesn't have that. I have some other n's in the problem, but they're inside of the nth power of what's going on. So again, this one kind of lends itself nicely to seeing that that's a good test to start with. So we're taking the limit as n goes to infinity of the nth root of 4n over 5n plus 1. We can do the absolute values if you like. It doesn't really matter. Why does it not matter? Anybody know? It's all positive anyway, so use them, don't use them. It doesn't affect anything in the end result. I'll write them as one step there, and I won't write them after that. All right, so as we're doing this, of course, the nth root and the nth power are inverse operations. So as I do that, and if the absolute values are not necessary, I actually just have 4n over 5n plus 1, right? That's nice. What does it approach? It's 4/5. Now we need to do one more step to show that, right? But it's 4/5, yeah? So we're going to multiply by 1 over n, top and bottom. So this is going to be the limit as n goes to infinity of 4 over 5 plus 1 over n, and the 1 over n is going to 0. So I get 4/5.
On the test, do we have to show that step?
For right now, yes. I know you can do it. I know you can. But I'm really glad you can just see it too. I mean, that's a valuable tool, of course. What was your question, Ethan?
So what step are you referring to?
He's referring to the step of multiplying by the 1 over n. Intuitively, I asked you all, what does it approach? And everybody said 4/5, I think. So it does, but you're just going to show it, okay? Yeah. And then, of course, 4/5 is, yeah, it's less than 1. You're going to say that too, by the way, okay? I know you know that 4/5 is less than 1. And so, yeah, it does converge, absolutely. So, yeah, by the root test, because you keep running into these problems. If I could just say you don't have to say it because it's obvious, well, it should also be obvious to me that you used the root test, right? I mean, you took a square root. But how much are we just going to not say? That becomes the question. So by the root test, yes, on the homework as well. By the root test, the summation from n equal 1 to infinity of 4n over 5n plus 1 to the power of n converges absolutely. All right, let's do another one. So this is summation from n equal 1 to infinity of n over 500 to the nth power. You think so, huh? We just might. All right, so we're going to do the limit of the nth root of n over 500 to the power n. Again, the absolute values on this one are not necessary, simply because it's positive values. Some of yours are going to be alternating series, and so again, it'll just eliminate the -1 to whatever power is, the nth or the n plus 1 or whatever it is as well. Okay, so this gives me the limit as n goes to infinity of n over 500, right? All right, so what can you tell me about n over 500? That's infinity, right? You betcha. So this is equal to infinity, which is greater than 1. Yeah, we don't have to necessarily say it on this one simply because the way they state number 2 with your root test in your book, which is not always the way it's written, but it's how yours is written, that if it's an infinite case, it's the second case already. So, yeah, so what does the root test say? It diverges.
Question.
Yeah.
Is the reason why we say, I just like noticing the definitions where it says that, like this converges absolutely before we could state that. Is that because when we're taking the square root, we're assuming that it must be positive?
Yeah, that's the only way it would work, yeah. And so if you remember too, converging absolutely had to do with absolute values being present, and so we were working with that within the root and the ratio tests. Yep. Yep. Okay.
What if it doesn't? What if we do it?
If it's inconclusive, it means that it wouldn't be using that test. Like you can't use it. You'd have to try a different test. So then maybe you decide, oh, look, it was also geometric. I could have done that. Or, oh, look, maybe an integral test would have worked on this one. And so you go back to the drawing board and try something again. It's kind of like when you're learning, integration rules, all the different integration processes. And you're like, oh, look, it looks like it's strict substitution. You're like, okay, well, that didn't lead me anywhere. Time to go back and try something different. It's like that. Well, I don't want you to spend 45 minutes on one, but we're actually going to talk about that now, to speak of. I want you to write this down, page 632 in your book. Really important. It has an excellent, and I'll pull it up here on the screen in a moment, but it has an excellent summary of the convergence tests. It's useful stuff for sure. Excellent summary of the different convergence tests. And so I'm going to pause the video. I'm actually saying this because we do have a couple people gone today. I'm going to pause the video, and if you guys will get a chance, if you don't have your book with you, it's fine. I'm going to pull it up on the screen, and we're just going to take a look at it together, okay? All right, so what we're going to do is we're going to use that table that we just looked at to answer a few questions, and you'll go further than this. We will go further than this on Wednesday. But we're going to name a method that can identify if the series converges. And we're just going to do a few of them. So the first one we're going to take a look at is n equal 1 to infinity of e to the n over n factorial. So, there was like 8 tests or something like that. I don't know if it was 8, but something like that on the other sheet. Which would you try on this one if you were trying to see if it converged or diverged? Ratio test is a good one to try. And there's actually 2 keys as to why it's useful. One, of course, is the factorials. I mentioned that before, right? I see a factorial, ratio test is a good choice. The other thing actually is this power of n. And so I know the power of n sometimes means root test, but the power of n is actually really nice when you do a ratio test as well. We saw it happen with that 6/5, right? It just left one of the 6/5 power in there and everything else reduced. So it's actually a really nice, clue as to using the ratio test. All right, let's try another one. Summation from k equal 1 to infinity of negative 1 to the k of 1 plus 1 over k over k. Yeah, it's alternating, right? Yeah, it looks like an alternating series test would be a good choice on this one. What else could you use? Is that what your question was?
Yeah. I don't know.
Well, ratio and root aren't going to work, right? Because I don't see any of those nice simplification kind of steps. I don't see anything that looks geometric on that, right?
Just find the limit as is.
You mean find the limit without the negative 1 to the k? Yeah.
Find the limit. Just use regular alternate series.
Well, what you have to remember is that a lot of our series only work for positive terms. So the fact that I've got a negative 1 to the n here was when we encountered our negative, our oscillating terms, some of them being negative, some being positive. And so some of those earlier on tests can't be used because of the negative 1 to the n, or n to the k in this case. Yeah, most of them were positive only terms. Let's try another one.
I was just saying, if we just use the regular alternating series, it solves it.
Yes, that's correct. It's a regular alternating series. You are correct. And like you guys said, I didn't circle it, but I will. This is the key, right? It's the negative 1 to the k power is the key of using that. How about n equal 1 to infinity of n to the negative 4 over 5? It's p-series. How do you know? Awesome. Because we can rewrite this as 1 over n to the 4/5, right? And so then p-series can be used to determine the convergence or divergence. Good job.
Can the integral series work with that?
It could. Yeah, you could integrate that, no problem. Sure. All right, let's do one more. Summation from n equal 1 to infinity of n squared e to the negative n squared. It should say cubed. There's a typo in my notes.
Integral?
It's integral, yeah. That's why I had to fix that. Yeah, this is an integral. Yeah, it is. I wrote it wrong and I tried to fix it and I didn't fix it very well. That's better. Yeah, it's an integral. In fact, if I did this integral, I'd need to use what in particular? U substitution, yeah. So this is a U substitution that we'd be using if I were doing an integral test on that one. Okay, I have a very short board work thing for you to do. You don't even have to be on the boards. You can just work in pairs together in your seats. What you're going to do, actually let me flip to this over here to the other side, is that the homework for this is on page 633. And the first part of it is I'd like for you to finish this board work. It's numbers 5 through 10, if I'm remembering it correctly. I didn't get it written down after I had made that decision. And then the part that would be done for homework is 13, 16, 19, 22, 25, 36, 39, 42, and 45.